Our key focus in Chapter 8 is going to be right triangles. We're going to look at right triangles and some different formulas and properties that we can use to find some different segment lengths. Today we're going to talk about some similarity that can occur in right triangles. Our theorem says, if the altitude is drawn to the hypotenuse of a right triangle. Okay, so for this theorem and our corollaries that follow, the picture is going to be really important. So we're going to draw a right triangle, but we're going to draw it a little bit different than we normally draw it. We're going to draw it so that it's laying on its hypotenuse, so that its right angle is up in the air. Usually we draw it so that the right angle kind of makes a straight up and down L, but here we're going to draw it so it's laying on its hypotenuse. It says if the altitude is drawn to the hypotenuse, and altitude is a height, so what we're going to do is draw down a height from that right angle to the hypotenuse. And an altitude is a height, and heights are always measured straight up and down. Like when you go to the doctor, they don't want you leaning, they want you standing straight up so they get your accurate height. So that altitude should be straight up and down, which means it creates right angles as well. So if the altitude is drawn to the hypotenuse of a right triangle, it says then the two triangles form. Well, when we do that, there's now really three right triangles in this picture. There is a right triangle over on the left-hand side. There is a right triangle on the right-hand side. And we started the problem with a right triangle. So the theorem says then the two triangles that are formed, the green one and the blue one, are similar to the original, the whole big purple one, and actually similar to each other. So before break, in Chapter 7, which was like a month ago, so it seems like a really long time ago, it was a long time ago, we talked about what similar means. Similar means that the angles are congruent and the sides are in proportion, that there's some ratio that matches with the sides. So like a blueprint, it's just a shrunken down version. The angles are all still the same, but the sides are just kind of shrunken down or blown up in some way. So this theorem says the three triangles in this picture are actually similar to each other, and we could set up some proportions to solve for those missing lengths. Our corollaries that follow give us the formulas that will help us find those lengths. So for these corollaries, I'm going to want that same picture drawn out again. So we've got that same setup when the altitude is drawn to the hypotenuse of a right triangle, so we have the same picture going on. It says the length of the altitude, that's that height piece, and I'm going to label it A. The length of the altitude is, in math, when we hear the word is, that's like an equals. So altitude is, or A equals, the square root of the product, what does product mean? An answer to a multiplication problem, so we're going to multiply square root of the product of the segments of the hypotenuse. Well, the hypotenuse is the side that it's laying on, and when we draw in that height, it kind of broke it into two pieces. So I'm going to call those two pieces B and C. And this formula says that the altitude is the square root of the product of those two segments or broken pieces of the hypotenuse. Okay, so the altitude, that height, which I labeled A, is equal to the square root, yesterday we talked a lot about square roots, of the product or the multiplication between the two broken pieces of that hypotenuse, or the broken pieces of the side that it's laying on. The second corollary says when the altitude is drawn to the hypotenuse of the right triangle, so when we have this picture, each leg, and there's referring to the legs of the original right triangle, so I'm going to label those D and E. It says each leg is, so D is and E is, the geometric mean. Okay, well that's a new term for us. It was actually defined in the other corollary. In the other corollary it says geometric mean is the square root of the product. Okay, that's the definition of geometric mean. square root of the product. So some of your problems tonight are going to ask you to find the geometric mean between two numbers. You're going to multiply them and take the square root. That's how we find a geometric mean. That's what geometric mean means, is to do a square root of a product. So in the second corollary then it says each leg is the geometric mean or the square root of the product between the hypotenuse, and that's the hypotenuse of the original triangle, and the segment of the hypotenuse that is adjacent or next to that leg. So the whole hypotenuse is B plus C. It says between the hypotenuse and the segment of the hypotenuse that is adjacent or next to that leg. So what's next to D in the picture?
A and B.
B specifically, the piece of the hypotenuse. And next to E would be C. Those three formulas are going to be extremely important in solving your problems tonight. For solving the vast majority of your homework problems, you will need to apply these formulas. So make sure that you have this picture drawn out the same way and that these formulas are written out, because they make a lot more sense for solving when they are in formula form than when they are in the word form of the corollaries. So please make sure you have these drawn out for tonight.
Will we have to memorize it?
Yes. Yep, for the test you will need to be able to duplicate this picture and formulas.
You would.
Alright, so for some examples on this, we're going to start with the same picture, except I'm going to draw it on its side, so that the original right triangle is drawn more like what we're used to seeing a right triangle, where it's kind of standing straight up. I'm going to label each of the points, or each of the vertices in there. And then given that angle R is equal to 30, how big will angle RSU have to be?
Say it one more time.
Given that angle R is 30, how big will angle RSU be?
60.
Why will it be 60?
RUS is right.
Because there is a right triangle in here. We've got a right angle up there, which defines 90, and inside of a triangle we need to have 180. So that leaves 60 left over for that angle S. Okay. Then how big is angle UST?
30.
30. Because we have a 90-degree corner there. We know part of it's 60, the other part will have to be 30. So you can probably guess what's coming. How big will angle T be?
60.
60. Why?
Equal 180. 90 plus
Equal 180. So we've got another smaller triangle there that we need to have 180 in, or you could actually look at the whole large triangle as well and still need to have 180. So our theorem said that these three triangles should be similar, and we, when we defined similarity, back in chapter 7, before break, we said all the angles should match up, and it looks like that appears. We've got all 30, 60, 90. So it looks like all the angles match up. It said sides should also be in proportion. We don't have any information about sides, but we did have something called angle-angle similarity that said if the angles match up, then that's good enough. We know these would have to be similar. So if I name the first triangle, the whole big one, RST, I should be able to name the two smaller ones as similar to the first one. And remember, when we name triangles, we don't randomly select how we want to do our letters. The order of the letters determines the relationship, so that they need to match. So if the whole big triangle is RST, let's name the blue smaller one. What angle is going to match with R of the big triangle in that blue one?
R.
R, because it's still there. It's still there, it's still 30 degrees. So 30 matches with 30. And the whole big one, RST, how big is S?
90.
90. So what letter of the blue triangle will match with that?
U.
U, because U is 90. And what letter will match with T? S, because that's the other letter in that blue triangle. Let's name the green one. In the whole big one, angle R is how big? 30. What will match with that in the green one?
S.
S is 30. And the whole big one, S is how much?
90.
90. What will match with that in the green one?
U.
U. And what's the third letter? T. Because that's the third letter in that green triangle. Okay, so we can name up these similar triangles that we know have to happen according to that theorem 8.1. The next type of example I want to look at, the directions will ask you to find a geometric mean between two numbers. Geometric mean was defined in the notes as being a square root of a product. We are going to multiply the numbers together and take the square root of them. So what is the geometric mean of 2 and 3?
Square root of 6.
Would be the square root of 6. We multiply them, take the product of them, multiply the numbers, 2 times 3 is 6, and take the square root of it. Always simplify square roots when possible, not just if the directions specifically say simplify, but it's just assumed that that is something we always do when we get a square root for an answer, is to simplify. Not give a decimal, decimals are not okay, but to simplify the way we learned yesterday, where we asked ourselves, are there any perfect squares that divide into this? So are there any perfect squares that divide into 6?
No.
So perfect squares, we said our numbers we can take a square root of, like 4. 4 doesn't go into 6. 9, well, that's already too big, and we passed it by. So this must be as good as it gets. What about the geometric mean between 2 and 6? That would give us what?
8. Square root of 8.
Product, not sum.
12.
12. Square root of 12. Does that simplify? Are there any perfect squares that go into 12?
Square root of 4.
Square root of 4, and that would leave a square root of 3.
2.
The square root of 4 is
2.
2. Square root of 3. Last one of this type, geometric mean of 4 and 25. Give us the square root of 100, which is 10. That's actually a perfect square itself. We just want to take that square root and get 10. Okay? Questions on geometric mean? The last type of problem we want to look at is going to use those formulas that were in the notes. So I'm going to use the picture that's actually the same exact picture as in your assignment. And we'll be given pieces of this and want to find other pieces. So for this, when you do these problems, I would suggest that you have the formulas in front of you. So I will write those out again. Along with kind of the standard picture that we used, where we labeled what each of these letters means. So for our first example, I'm going to give you some pieces of this, and we'll be looking for another piece of it. So let's say that LM is 4, MK is 8, and JM is unknown. That's what we want to find. We need to first determine which of these 3 formulas would be helpful to us here. So how can I tell which formula I would want to use?
Would it be the A equals B, square root of BC?
Yes, it'd be the first one with A, B, and C. What we want to do is look at our starting picture where we have our information, and then look at kind of our general or standard diagram and say, what stuff do we know or want to know? Where do I have labels in here? So I know A, I know C, and I want to know B. And I want to use the formula that uses that information. And the one that uses letters A, B, and C is the first one. So we're going to, for this problem, use the first formula. Then we're going to plug stuff in where it goes. So A, we were given, is 4. B is labeled x, and C is labeled 8. And we want to solve this for x. Yes.
Could you simplify the square root down to the square root of 4, square root of x, square root of 2?
Sorry. No, we cannot break up. Well, you could. It's just not the most helpful way. If we're trying to solve for x and it is underneath the square root, it's kind of trapped right now. So we can't do anything with the x itself until we set it free from its cage. We have to get rid of that square root. How do you think you undo a square root? In every kind of math, there should be a way to undo it. Like if you add, you can undo adding by subtracting. If you multiply, you can undo multiplying by dividing. So if I've square rooted something, I have to have a way to undo the square root. And what do you think that would be?
Square.
Square. Squaring and square rooting are opposite operations. So what we're going to do is square both sides of this equation. 4 squared is 16. And when you square a square root, they cancel each other out because they are opposites, just like adding and subtracting or multiplying and dividing. They undo each other, and it gets rid of that cage, and it sets that x free. The x is not alone, though. It's still with an 8. How do I get rid of that 8? By doing division. It is multiplied, so we undo multiplying by dividing. So x equals 2. Yes.
Is it just coincidence that b divided by a
Yeah.
equals c?
Don't just divide the numbers.
Did you say that?
Good pattern recognition, but it's not actually a pattern. Let's do another example of this.
Why did you do the 4
Why did I do what?
Square 4.
To get rid of the square root. Whatever you do to one side, you must do to both sides. So if I wanted to get rid of the square root by squaring, I have to square both sides. For our next one, let's say that JM is 3 and MK is 9, and let's find JL. So then I need to determine which formula I need to use. So I'm going to look at the standard picture and say, okay, I know B and C, and I want to know D. So which formula should I use?
Second one.
The second one, because that's one that has letter D in it. So if I want to find letter D, then I better use a formula that has that letter in there. So we're going to plug in what we know then. D we don't know. That's our x. Square root of B is 3 times B is 3 and C is 9. Order of operations says we have to do what is inside of parentheses first. So we want to combine the 3 and 9 together and get 12 first. Then we can multiply, and 3 times 12 is 36. And then we want to simplify roots. Square root of 36 is 6. Questions?
Why is the answer not x equals the square root of 6? Just 6?
Because the square root of 36 is 6. The square root of 36 isn't the square root of 6. The square root was already done.
Okay.
That's what changed the 36 to the 6. That's a common mistake. Students just keep on writing square root every step along the way, even after it's already done. All right, let's do one more of this type. Let's say that this time JL is 9, JM is 6, and we want to find MK. So we line up with the starting picture and say, what do we know or want to know? We know D, we know B, we want to know C. So which formula should I use?
The second one.
The second one, same one as last time because that's the one that has letter D in it, and we know something about letter D. So we'll fill in what we know and what we want to know. D is 9. Square root of B is 6. B is 6 again. And C is X. We are solving for X and it is trapped under the square root. So when it is stuck in a cage, we can't do anything with it until we get rid of that cage or get rid of the square root. How do we get rid of a square root? Square. So we're going to square both sides. Squaring 9 gives 81. Squaring the square root just takes it away and leaves exactly what was underneath. Okay, we don't do anything to the numbers underneath. It just takes that cage away. It just takes the square root away from both sides. Now what do we need to do? Distribute. So we get 36 plus 6x. Then what do I do? Subtract 36. 45
Divided by
is
6.
6x. And divide by 6. And we get
A number equals X.
7.5 equals x.
Can we just leave it 45 cents?
You could reduce 45 6. They both reduce by 3. So I would say 15 over 2 would be okay, but not 45 over 6. Questions? All right, your assignment for tonight is from 8.1, as written at the bottom, except you already did problems 1 through 15 last night, so that means you get to begin at question 18, because you already did the first group of problems there. So 18 and 21, those would be the only multiples of 3 there, and then the rest as written.